In this video, we'll talk about how to incorporate binary information in a regression model and also talk about how to interpret the coefficients. So let's take the simplest example here where we have wage as our dependent dependent variable and binary information on gender captured by this variable female on the right hand side. So we're basically trying to explain wage using a variable female, which is telling us about how does gender matter for wages. Okay. So notice the only thing that's different here from what you've seen before is that the intercept remains specified as beta naught, but the coefficient here is denoted by delta naught. So we're going to use a bunch of deltas whenever we have binary information or we are dealing with dummy variables in our regression. Now, assuming that the zero unconditional mean assumption holds, we can write out the expected value of wages given this binary information on gender as this. Now notice, because female only takes two values, 0 and 1, we can actually write out the expected value for males in this way. So all we do is take the expected value and we plug in 0 for female. This is the case for males. Okay, so when we do that, we get beta naught. So we're basically saying the average wage for men is beta naught, but then for the female case, when we plug in the value of 1 for female in that expression, we get beta naught plus delta naught. So we're basically saying that the average wage for women is beta naught plus delta naught. Okay, so now we can basically rewrite what delta naught is, since we know what beta naught is. This is the average wage for men, and what the average wage for women is. We can take the difference. The difference between these two is going to be delta naught, right? So delta naught is basically giving you the difference in the average wages between women and men. So delta naught is not really a slope. It is just the difference in the average outcomes between the two groups that are specified here. Okay, so it's important to remember the interpretation here. And sometimes we might also want to denote delta naught as just the difference between the average wages between females and males, right? So this is just another way of writing this out for the sample. Now let's take an example and see how we can do this in R. So if we, assuming that you have the Woolrich package installed and the Tidyverse package installed, you can take the dataset GPA2. So maybe you need to do this before. So you need to say data GPA2 before this. And then we can take, once that's loaded in your working directory, then we can take GPA2 and we can summarize, create mean F as the mean of females and mean M, which is mean of males, as the mean of 1 minus females. So here you get, this is 44.9%. So this is telling us about 45% of our sample is females and 55% is males, right? So if you add these up, this should be equal to 100% because these are the only two categories. Now we can also regress wage on female, right? That's what we were trying to do before. So remember, if there are two categories for that variable, In other words, if female only takes two values, 0 and 1, you only need to incorporate one independent variable in your regression, okay? So that we don't fall into the dummy variable trap. Because you can basically discern what's going on with males just on the basis of this regression alone, like we saw in the previous slide. So here we can see that the coefficient on female is negative, right? And this is significant. And the estimated difference is very large, okay? So here we saw that women earn about $2.51 less than men per hour on average, right? Of course, we haven't controlled for anything else. But remember that in your sample, you might find that there are some women who earn more than some men, and that's totally fine because the regression analysis only tells us the differences between the two groups in on average, right? So remember, the way to look at this coefficient is it's giving you the value of delta naught, and delta naught is this coefficient on female. So it's telling you the difference. It's not telling you what the average wage for females is. It's telling you what is the difference between the average wages for females versus males. So in other words, what our simple linear regression analysis here has allowed us to do is a simple comparisons of means test, right? So if we were hypothesizing, if our null said that the mean wages for females is equal to the mean wages for men on average, then we basically have rejected that hypothesis or that null hypothesis because our t statistic on female is very high, right? The t statistic is really high, and this is significant at the 0.1% level. Now, of course, there's a drawback in utilizing such a simple linear regression because we haven't controlled for factors that should affect wage, right? So there could be workforce experience and the level of education that would affect wages, right? And if in our data sets, if women have on average less experience and less level of education, that could explain the difference in average wages that we're capturing. So there might be other confounding factors that we haven't taken into account. So let's try to do a simple addition or make an addition to our regression by adding in experience, right? So notice here I keep the same notation as before, where delta naught is capturing the difference between the two groups. So I'm keeping that as delta, but I'm denoting the coefficient on experience by beta 1. Okay, so the interpretation of this delta naught now is going to be that it is measuring the difference between females and males when we hold experience fixed. Another way to write out delta naught, if we had the previous regression, would be to think about delta naught as the difference between the wages for female holding experience constant, difference between the wages for females and males holding experience constant. So experience 0 is any level of experience, which is going to be held the same for females and males, okay? And so we can see when we do this analysis, we can see that now the coefficient on female is still negative and very, very significant, and it drops slightly to $2.48. Okay, so here we still see a difference that is significant and is a little smaller. Okay, now there's another problem with this model because we are assuming that there's a common slope on experience for both males and females. Okay, and we are basically denoting that by beta 1, and we estimated that to be about 0.26. So we could try to think about a case where the effect that experience has on wages depends on whether you are male or female, right? And this model doesn't allow for that. So this model is not allowing the effect of experience on wages to depend on the person's gender, so or sex. So we can basically allow for that by interacting female and experience. Okay, so the drawback of that model that we just saw was that we will capture, if we try to capture experience on the x-axis and wages, we're basically saying that there exists some sort of a difference between men and women, but the effect that experience has on wages is the same for both men and women. Okay, and so here this should be, my apologies, this should be 48. So $2.48. That's the difference, right? And the blue line is for men and the red line is for females. We can always think about adding more variables, and then, the picture is going to be harder to draw, but we can control for the amount of education by the number of years in college, and then you would notice that the gap keeps shrinking, but it's still statistically significant. Now, it's important to remember that in previous regressions, we have used males as the base group, right? Or the benchmark group or the reference group, right? So the category that we will leave out, so any category that we are leaving out in our regression is going to be our base category or our reference category. So when we interpret the coefficient delta naught hat on females, we're basically saying this is the average difference between females and the category that was left out, which was males. Okay. Now, we can always switch that around if you wanted to. Instead of females, get the coefficient on males, for instance, you would just regress wage on males, and you would get the same answer, or the interpretation would be very similar, but delta naught is going to flip the sign, right? So here you would, if you were finding that the coefficient was negative $2.48 previously on females, now it's going to be positive for males. Okay, again, the interpretation is going to be the same, that men make, or males make $2.48 higher on average than females, ceteris paribus. Okay, so the coefficient on the dummy variable changes sign, but it remains the same in magnitude. Okay, and remember that if you are regressing wage on males, then the category that's the benchmark or the reference group or the base group is females. That's the category you left out. Okay, so now remember that whenever you have two categories, females and males, putting both females and males in the equation is redundant. If we have two groups, we only need two intercepts. One intercept is being captured by beta naught, which is telling you what's going on with males if you have female in the regression, right? So if you're writing out something like this, you do not need to have another variable here, because this variable itself captures what's going on with males, okay? And these two together tell you what's going on with females. So basically you plug in the value. So female equals 0 for males and equals 1 for females, right? So we get that. Okay, and even if you made a mistake, the statistical software would typically drop one of the dummies. Okay, so if you did make a silly mistake like that, hopefully you don't make that mistake. But if you did, this any statistical software, whether it's Stata or Python, any software would drop that redundant category. Okay, so if you do that, typically the statistical software is avoiding the so-called dummy variable trap, which typically results from putting too many dummy variables to represent a given number of groups. Okay, so if you put in 2 variables, if you did this, then something would be dropped, okay, whether it's females or males. Okay, so because these are intercepts, these are estimated, the intercept beta naught is estimated for the base group. We only need one variable that distinguishes the two groups.